In this video, we are going to implement the stable fluids algorithm by Stem in order to solve the incompressible Navier-Stokes equations, creating this wonderful plume in roughly 200 to 300 lines of code. Let's get started. Hi and welcome to this new video. Stable fluids is an algorithm based on a paper by Stem released in 1999. It is still ubiquitous in computer graphics if you want to create realistic fluid flow motion. It is called stable fluids because it is an algorithm that is unconditionally stable. So you can choose arbitrary large time steps, and also the kinematic viscosity of the flow can be chosen freely. Here we have the Navier-Stokes equations consisting of the momentum equation and the incompressibility constraint. However, we won't be seeing it in that form too often in the rest of the video. The problem we are going to look at is a closed box. So we have a unit square domain where we prescribe zero Dirichlet boundary conditions, or in other words, the velocity is zero on the boundary and the fluid is at rest in the beginning. And then we have a forcing happening over some time in the beginning, which creates an upwards motion in the fluid. And then by the effects of the incompressible Navier-Stokes equations, we are getting the plume effect that we've seen in the intro video. So how does this stable fluids algorithm work now? I'm trying to follow the paper by Stem as closely as possible. So there he outlines 4 major steps. So in our case, again, we start with a zero velocity everywhere, so the fluid is at rest. And remind yourself, a velocity in 2 dimensions is also a 2-dimensional quantity. Then, in the first step, we will add forces by multiplying our force contribution with the time step length and adding it to the starting velocity. In the second step, we account for the nonlinear convection in our Navier-Stokes equations. We do that by a so-called self-advection step. Sometimes you also call it semi-Lagrangian. And it works like that we set our convected fluid, here W2, to be the non-convected fluid, but at rest at points that are traced back on the streamlines. That sounds a little bit strange now, but we will look into this in more detail. The advantage here is, due to us backtracing on the streamline, we are unconditionally stable with the self-advection. The third step is a diffusion, and here we will apply the diffusion implicitly. This means we have to solve a linear system of equations, and we will do that in a matrix-free fashion by conjugate gradient. You will also see that later in the video. This approach is also unconditionally stable, and then by the fact that the convection and the diffusion are performed unconditionally stable, the entire algorithm will be unconditionally stable because these are the 2 steps that usually introduce instabilities when solving the incompressible Navier-Stokes equations. Then we have a 4th step, which is due to our incompressibility constraint. In the first substep, we compute a so-called pressure correction, or in other words, a pressure, and we do that by solving a linear system of equations. That is also called the pressure Poisson equation, by saying that a quantity, which turns out to be the pressure, in a Poisson equation has a right-hand side that is equal to the divergence of the diffused field. And if we then have this pressure from the equation, we can correct our velocities and then they are incompressible. The solution to the pressure correction is again a linear system which we will be solving matrix-free using conjugate gradient. And the last step is to advance to the next time, and then we repeat this over and over depending on how many time steps we want to do. Just a quick note, we won't be explicitly prescribing boundary conditions here. This is done indirectly, but if you want to adapt this to your particular scenario, then you might have to take care here. Then let's get started by first importing all the necessary packages. We need NumPy for our computations, so we do import NumPy SNP, and then we need SciPy components, and we need in particular scipy.sparse.linalg, and I will import this as sp.linalg, sparse linear algebra. Then we also need the interpolation package from SciPy, import interpolate. Then we want to visualize our results, so we do import matplotlib.pyplot splt. And then I have 2 more optional dependencies, so I will put this as optional. we need C measure. I really like their color maps, but this is of course optional. And then we also need TQDM, which is a simple progress meter, but you also don't have to use it. Then let's start by defining some constants. So first we have a domain size, which will be 1.0 in each axis. Then we will be having 41 points in each axis. And then let's perform 100 time steps with a time step length of 0.1. Let's set the kinematic viscosity to 0.001, and we will set the variable max iter CG for the maximum iterations in the conjugate gradients algorithms to none, but I will come back to that in a second. Then let's define a main function and leave it empty for a second, and let us implement a main switch such that our file is only executed by the Python interpreter. And then we can start with our main function. Let's first infer the element length, which will be the domain size divided by the number of elements. And since we will be having 2 boundary points in each axis, we do number of points minus 1. Then let's define the shapes of the objects that we will be using throughout. So we have vectors, which are defined in 2D, and we have scalars defined in 2D. So let's start with a scalar shape. And if we have a quantity that is discretized on our computational mesh, then this will have the shape of number of points by number of points. And the total number of degrees of freedom will therefore be n points squared. Then let's do the same for a vector shape, which will be n points by n points by 2. And correspondingly, the vector degrees of freedom is the number of points squared multiplied by 2. But then we can discretize in x and y direction. So first in x by using NumPy dot linspace from 0 to domain size with the number of points. And we do the same in y direction by saying from 0 to domain size and then the number of points. And then we can use these two discretizations to create a two-dimensional mesh. So we do x, y is np.meshGrid, and then plug our x and y in here. And now I want to use a different indexing than the default one. So I do indexing ij. And this might seem a little bit strange at first, but it helps us to make our differential operators later on more logical. So let me add a comment here using the ij indexing makes the differential operators more logical. Of course, it's a little bit subjective, and just a note for you that you should take care when you plot this with matplotlib, because it can be a little bit picky about the indexing here. Then let's use the x and y positions of our mesh in order to create a coordinates object. And these coordinates will be of the same size as the vector shape, because we will be having something batched over x and y, and we will be having 2 coordinates per point basically. So what we do is np.concatenate, and then we will be having our x grid and axis at all the points, and I will add a new axis at the very end. Right now x is just an n points by n points tensor, and now we add a proxy axis in the end such that we can easily concatenate over that. And let's do the same with y. Add a new axis here, and then we concatenate over the very last axis. And that of course then gives us the coordinates object, which is of n points by n points by 2. And now before we start our main time loop, let's define the forcing function, which we have left out so far. For this, let us create the function forcing function, which takes a time and a point in space. And then I want to make this function look as following, that we have a time decay, that this forcing only happens in the first 2 seconds. And then we also want it only to happen within this bit of the lower center of our domain. So let's first define a time decay and let this be np.maximum of 2.0 minus 0.5 times time and 0.0. And this will basically be a function that is a linear function from 0 to 4, and that is 0 afterwards. And then we can define our forced value, which will be the time decay multiplied. And now we want to look where we are in the domain. Therefore we say numpy.where, and I want to introduce the following condition where we say, is the x coordinate greater than 0.4 and is the x coordinate smaller than 0.6. So we want our force value to only be applied in the interval of x from 0.4 to 0.6. And then let's check on the y coordinate. This one shall be greater than 0.1 and it also should be smaller than 0.3. And now I think you can somehow imagine where we are in our domain. And if the point is within this patch, then the forcing shall be upward facing, so 0 in x and 1 in y. And in case it is not in there, we just have a 0 contribution. So once again, when we are in this patch, then we have upwards facing forcing, and if we are out of it, then no forcing at all. And then let's return the forced value. The problem with this forcing function is that it only applies to one point, but we want to call it batched on all the points that we have in our mesh. Luckily, NumPy has a vectorization function for us, so that we can create a forcing function vectorized. And it works as following, in that we say np.vectorize, and then we take our I function to be forcing function, that's what we want to vectorize, and then let's say the signature for this function is that it has a non-dimensional object in time. This will just be a float, and then we have a d-dimensional object in point, so this is a two-dimensional point, and right now it returns a two-dimensional point, or in other words a vector again, and then we want it to be vectorized over this axis here. Okay, then let's go start with our time loop. First we have to define the velocities at the previous iteration, and we wanted to start at rest, so we have a numpy.zeros, which is of the vector shape, and then we have a current time to be 0, and then we just perform our time loop with tqdm in order to get a progress meter of the number of time steps. And then first step, we advance the time by time step length. And then let's first gather the forces which are applied at this current point in time. Let's call this forces and say that is the forcing function vectorized applied to the current time and on the coordinates. And then we can have our very first step in the algorithm by your stum, which is to apply the forces. I will call the resulting objects velocities forces applied, and it will be the previous velocities plus the time step length multiplied with the forces. That's great. First step done. Let's go on to the second step, which was to do the convection. So we want to do the nonlinear convection, and that is equal to self-advection. For this, let us implement a function which performs an advection. So let's go up here and call this function advection or advect. And this takes a field as well as a vector field. And it works that we advect the field alongside the vector field. For this, we will first define so-called backtraced positions. And in the original paper by Jostam, this is performed by integrating the streamlines backward in time using an ODE integrator. He recommended to use Runge-Kutta free indicator. But here, for simplicity, we will just make one Euler step backward in time, which is also the version that he introduced with his paper on real-time fluid dynamics for games. For this, we will use a clipping, and I will explain that in a second. And then the main operation is to say we are at the current coordinates. These are the points in 2D space that are associated with the velocities, or where we have our velocities discretized. And then we subtract the time step length times the vector field. So in other words, we are taking our coordinates, let's say for instance 0.5, 0.5, and then we go backwards along the streamline with one simple Euler step. And then we clip this to be within the domain, because potentially with this we could leave our domain. And if that is the case, then we will just be on the boundary. And now the big clue is that we say that our vectored field is the field at these particular positions. And now, of course, these backtraced positions could not match with the positions at which we are discretized. So we need to do an interpolation. And we can easily do that with a SciPy routine by saying interpolate.interpn for interpolation in n-dimensional spaces. And we say points are equal to x and y. So these are like our one-dimensional discretizations. Then the values in 2 dimensions are given according to the field. And then the points at which we are querying, these are the backtraced positions. And that should return an advected field, which we can also return as the function here. With this function for the advection down, we can go back down here and say that velocities advected equals advect, and then say field is equal to velocities forces applied, and the vector field is also equal to velocities forces applied. And that is the big clue of this semi-Lagrangian step, that we say that we self-advect. So we advect our velocity field alongside the velocity field itself. And then we can go on to the third step, which is diffusion, which is to diffuse the vector field. And in order to do the diffusion, we need to solve a linear system of equations. For this, we need the Laplace operator. Let's go above the time loop, and then let's put the Laplace operator here. So we define a function called plus, which takes a field, and then we have a differentiated field, which will be zeros like our field, and then we fill the interior points of that field. So in other words, the differentiated field, or the Laplace applied to the field, will be having zeros on the boundaries. And that is what I meant by we are implicitly prescribing the boundary conditions that are homogeneous Dirichlet. Let's start. For this, we need to take the field and go back one step in x, and take the interior points in y. We take the interior points in x and go one step backwards in y direction. And then we subtract 4 times the interior points. And then we have to go one step forward in x. So we do plus field and say from 2 all the way to the end. And then the interior points in y plus field and then the interior points in x, and then one step further in y direction. And then let's divide that by the element length squared in order to get our discretized Laplace operator, and we return the differentiated object, and then we have a Laplace operator. Okay, the Laplace operator is bringing us one step closer to solving the diffusion linear system, but we want to solve it in an implicit way. So let's define an operator which is related to the implicit discretization of a diffusion. So for this, let me go down here, and I will call that diffusion operator. And in essence, this will be the function that is called within the conjugate gradient routine that we are then using to solve our linear system. This is called matrix-free, because we are not solving a linear system by explicitly building the matrix, but we are defining how the matrix acts upon vectors it is multiplied with. So the diffusion operator therefore also applies to an flattened vector field. So we say vector field flattened, and by flattened, I mean we have our dimensionality contracted into one axis, because we started off with a quantity that has number of points in x, number of points in y, and 2. And this will now be contracted all into one vector. So in order to define the differential operator, let us reshape it and call this the vector field, which will be vector field flattened, reshape it into the vector shape, and then we call this diffusion applied, which will be, in the implicit sense, vector field minus kinematic viscosity divided by time step length multiplied with the Laplace operator on the vector field. And then we can return that. So we return diffusion applied, but we have to flatten it again in order to be a vector. Now we have everything we need in order to solve the linear system. For this, let's go down and define the velocities diffused to be solution to a linear system, which we compute by sparse linear algebra .zg for conjugate gradient. And the A matrix or matrix-free approach is given by a linear operator by saying sparse linear algebra .linear operator, which has the shape. So we have a function that is representing a matrix or the effect of a matrix. Now we have to define how a dense matrix shape would be. And that would, of course, be vector degrees of freedom by vector degrees of freedom. And then the matrix vector operation, which is representing the effect of the matrix, is given by the diffusion operator. The right-hand side of this linear system is the advected velocities. So velocities advected, but we have to flatten it into one long vector. And then let's also fix the maximum number of iterations to max iterations CG. This call will return the solution to the linear system as well as an info tuple. So we just want the solution. So I will just take the 0th element of the returns. And then let's reshape it into the vector shape. That is because, of course, it will also return it in the flattened vector shape. So this is the diffusion step. Now we have to make sure our fluid is incompressible. So we do first 4.1, which will be computing a pressure correction. And for this, let's go up to the steps that we have to take. So the correction is defined over the Poisson equation of the pressure, where the right-hand side is the divergence. What do we have to do now? So we have to define the divergence as well as another operator for this Poisson equation. Let's start by defining the divergence. So I will go below the Laplace and say, well, we do the divergence, and divergence is a contracting operations. So it makes a scalar out of a vector and a vector out of a matrix. Here in our case, we just want to apply it to vector fields. And the divergence needs partial derivatives. So we also need to implement them. And we need partial derivatives in x and y direction. So let's do partial derivative in x, which takes any field, can also be a scalar field, and say that the differentiated object is again a zeros-like tensor. And here we are again implicitly prescribing our homogeneous Dirichlet boundary conditions. And then we say the differentiated object in the interior points is given as, and here we want to use a central differencing scheme. So we say field going one step forward by saying 2 all the way to the end, and the interior points in y minus field, and then going one step back, which is 0 to the second to last element, and then all the interior points in y. And then for the central difference, we have to divide that by 2 times the element length, and then we can return our differentiated object. Let's do something similar in y direction. So I will just copy that and say we have the y direction here. And for the y direction, we of course have to perform these steps here in the second index. So we will just keep the interior points in x direction. Now let's use the partial derivatives to define the divergence. And for the divergence, we will add up the partial derivative of the first velocity component with respect to x plus the partial derivative of the second velocity component with respect to y. So let's define divergence applied, and that one will be the sum as that first partial derivative in x of our vector field, but we don't want to apply the derivative to both components, but only the zeroth component. So we use this ellipsis structure, which selects over the two batch axes that we have, all entries, and then the zero component or zero velocity component. Plus partial derivative in y applied to the vector field with all components over the batch axes, and then the first velocity entry. And then we can return divergence applied. Okay, going up here, we see now we have an operation that yields the divergence. Now we need an operator for the Poisson equation. So let me define, similar to the diffusion operator and Poisson operator, def Poisson operator. And this one can take any flattened field. In our case, of course, the pressure field will be a scalar field. And similar to the diffusion operator, it will first reshape it into its tensor shape. So let's take the field and say that is the flattened field reshaped into the scalar shape. And then we say Poisson applied is just the Laplace operator applied to the field. And then we return Poisson applied, and we have to flatten it, of course, back into a vector. Okay, that should be sufficient in order to solve the pressure Poisson equation. So let's go down and say that the pressure is sp_linalg dot dg again, and A will be sp_linalg dot linear operator again. And now the shape is, of course, scalar decrease of freedom by scalar decrease of freedom. And the matrix vector routine is given by the Poisson operator. Then the right-hand side to this linear system is the divergence of our diffused velocities. So velocities diffused. Of course, we have to flatten it into a vector. And then let's also fix the number of iterations here into max iter CG. Similar to before, this will return an info tuple as well, which we will discard and then just reshape into the scalar shape. Now we have the pressure, which we can apply for our pressure correction. So let's look at the steps again. And here we see that the corrected velocity is the diffused velocity minus the gradient of the pressure. But we don't have a gradient operator yet, so let's also implement that one. So we go after the divergence and let's say the gradient, which takes a field, and that is an operation which increases the tensor rank. So it creates a vector out of a scalar, which of course makes sense. Otherwise we can't correct our velocity fields. So we say gradient applied will be np.concatenate. And for this, we take the derivative in x. So we do partial derivative in x on our field and the partial derivative in y on our field. And now the field is still in its, for instance, if it is a scalar, it is still in scalar shape. So it just has two axes, and we want to create a new axis by concatenating the two derivatives. So let's add a proxy axis here, np.new axis, by using the ellipsis operator. And then let's concatenate over the last axis. And then if we enter a scalar shape, we get out a vector shape. So then we can return gradient applied. Okay, that should be sufficient in order to correct our velocities. That will be step 4.2, where we correct the velocities to be incompressible. So we say velocities projected because mathematically speaking, we are projecting into a certain function space. And that one is given as the diffused velocities minus the gradient of the pressure. And then we can advance to the next time step. So advance to the next time step and say the velocities at the previous time step are the projected velocities. And this routine will then solve the incompressible Navier-Stokes equations, but we might also be interested in visualizing it along the way. For this, let me go again in front of the time loop here and start by doing some styling operations, say plt.style.use, and I want to use a dark background. And then let me also define the figure in which we want to plot that, which has a figure size of 5 by 5 inches with a pixel density of 160. That looks nice on my monitor. You might have to adjust this if you're using high resolution monitors. And then we want to plot what we have here. So let's say plot. And for the start, let's just plot the quiver plot by saying x, y, and then the projected velocity is x component, and the projected velocity is y component. Then we will use plt.draw in order to live update, and then plt.pause for a small amount such that the buffers are swapped. And then we can do plt.clf to clear the figure. Then we can run it. So let's bring up the terminal and say Python stable fluids. So, and then we see, oh, well, it's all black. So that's probably because the arrows are black. So let me try to cancel that. And now we have to change the quiver plot to use gray colors maybe. So let's do dim gray. So light gray. So let's see how it works this time. And it seems to be a bit too diffusive here. So let's check the diffusion operator. Maybe there we have another mistake. Let me see. So here, of course, that should be a multiplication instead of a division. And then if we run it again, yes, that is close to what I would be expecting here. So we see the velocities going upwards and it's creating this swirly motion of the plume. And then as time goes on now, you see it is getting a little bit more diffused, but it keeps rotating in that sense. Of course, that's not the plot you've seen in the intro. So let's create that one. And there I visualized the curl, so which is the swirliness of the field at that position. And in order to get the curl, we need another differential operator, which I will just call the curl2D, because usually curl is an operation that only works in 3 dimensions. But here, since we only have a 2-dimensional velocity field, we are only interested in the perpendicular rotation, which is this of a hypothetical third axis. So it takes a vector field, and then we have curl applied, which is the summation of the partial derivative in x of the y component minus the partial derivative in y of the x component. So let's do partial derivative in x of the y component of the vector field minus partial derivative in y of the vector field's x component. And then we can return curl applied, and then we can call it in our plotting routine so that we have curl is this curl2D operator on the projected velocities. And then let's plot the curl by the help of a contour plot. So do plt.contourf, and this contour function takes x and y again, and then also the curl object, which of course here is just a scalar field because we contracted the dimensions down in the third axis. Of course, in 3D, it keeps the dimensionality. So let's see how that looks. So let's rerun it. And then we should be getting that one here, which is highlighting parts of positive and negative curl, because here we are rotating clockwise and here counterclockwise. So that is changing the color of this contour plot here. The first step might be to use a diverging color map instead of a sequential. So here you could use any from Matplotlib, but I want to use one from this CMeasure package. So if you don't have that installed, you have to replace that with another one. And I think the redshift is really interesting. And then let's run this again and see how this one looks. So that's getting closer to what we have in the intro. We still have it a little bit discrete. So maybe let's increase the number of isolines that the contour plot is creating. So let me close that one and say the number of levels is 100 so that it's smoother. And then we can take a beautiful look at it. And that's what you've seen in the intro. And you might also notice that now the iteration count is going down so that we are doing less iterations per second. In other words, it is not real time what we are doing here. So this is always something that you have to keep in mind. And there are possible tweaks here. Of course, you can ignore the plotting and then it will work really fast. Or you could also adjust the number of iterations for the conjugate gradient. Let's finally add an plt.show statement here so that the plot is kept after the simulation finished running. And then let's look at the plot again. So we have the forcing introducing this upwards velocity. And then due to the incompressibility, we are getting swirls, one clockwise and one counterclockwise. And then due to the fact that we are in the box, the fluid can't escape. So it has to swirl here. And then we see that by the diffusion, the color should decrease in intensity over time, but we set the kinematic viscosity quite low, so this will take a lot of time. Therefore, let's just play around, and I would also encourage you to play around with it. Let's crazily increase the viscosity, and then we should see that it is no longer going upwards because now the flow is just so viscous that all the energy that we are introducing is dissipated quickly. And now we also have some artifacts here. These are because of the way we plotted, but interestingly, you can play around with it. And here you also see it will actually become unstable. It's super interesting. And I just want to highlight the reason why we can still have instability. And that is just because we are using such a simple advection routine. So let me go to the advect one here. So the one that is proposed in the paper by Jostam is to use a proper streamline integrator. And here we just did one Euler step. So in order to ensure full stability, we also need a more sophisticated ODE integrator here, but which I omitted for simplicity. So let's change the viscosity once again to the original one. So that is this value here. And then let's run it again. And let me then finish off the video. I hope you enjoyed it. Feel free to download the code from the video description and play around with the parameters. Maybe also build a different scenario. Then please also consider you have to actively prescribe boundary conditions. If you enjoyed the video, then please consider liking and subscribing and write a comment if there's anything unclear. Here you will now see similar videos, and I hope to see you in the next one.